the probability of x of t is equal to 1. This is equal to the sum of probability of n between 0 and t is equal to k, where k is an odd number. So this is equal to the sum of k from 0 to infinity, the e to the minus lambda t times lambda t to the power 2k plus 1, 2k plus 1. So this is equal to the e to the minus lambda t times, when k is equal to 0, is equal to lambda t over 1 plus lambda 3 lambda t to the power 3 plus dot dot dot. And we know this is the Taylor expansion of sine h lambda t. So we have the p of x of t is equal to 1 is equal to e to the minus lambda t times sin h lambda t. And problem B is find the expected value of x of t. This is equal to the x of t times the probability of x of t is equal to 1 plus x of t times p of x of t is equal to minus 1. Here x of t is equal to minus 1. Here x of t is equal to 1. So we have e to the minus lambda t times sine h of lambda t plus no, minus. It should be minus 1 minus e to the minus lambda t sine h of lambda t, and is equal to minus e to the minus 2 times e to the minus lambda t sine h of lambda t minus 1. Sine of h lambda t is equal to e to the lambda t minus e to the minus lambda t over 2. So this term is equal to e to the lambda t minus e to the minus lambda t times e to the minus lambda t. This is 1 minus e to the minus 2 lambda t. Minus 1 is totally the expected value of x of t is equal to minus e to the minus 2 times lambda t. Now we need to find the autocorrelation of T1, T2. This is equal to the E of xt1 times the complex conjugate of xt2, which is equal to itself. We know x of t1 and x of t2 can be, there can be 4 combinations. First is xt1 is equal to 1, xt2 is equal to 1. Second is xt2 is equal to minus 1, xt1 is equal to minus 1, xt2 is also equal to minus 1, and xt1 is equal to 1, xt2 is equal to minus 1, and xt1 is equal to minus 1, x of t2 is equal to 1. So the expected value of xt1 and x of t2 is equal to 1 times the probability of x of t1 is equal to 1, x of t2 is equal to 1, plus probability of x of t1 is equal to minus 1, and x of t2 is equal to minus 1, minus 1 times the probability of x of t1 is equal to 1, x of t2 is equal to minus 1, and plus the probability of x of t1 is equal to minus 1, and x of t2 is equal to 1. The probability of x of t1 is equal to 1, and x of t2 is equal to 1 is equal to the probability of x of t1 given x is equal to the probability of xt1 is equal to 1 given x of t2 is equal to 1 times p of x of t2 is equal to 1. We know this is mean the points between 0 and t2 is odd number, and this is means the points between 0 and t1 is an odd number too. So we know the points between t1 and t2 is an even number. So this is equal to the this is equal to e to the minus lambda for t2 minus t1 times cos h of lambda of t2 minus t1. For some reason, same procedure, we have p of x of t1 minus 1, p of x t2 is equal to minus 1 is equal to e to the minus lambda of t2 minus t1 sine cosine h of lambda of t2 minus t1 time here we need time this guy is equal to e to the minus lambda t2 times sine sin h of lambda t2, and here we need to multiply the e to the lambda of t2 cos h of lambda t2, and the probability of x of t1 is equal to 1, x of t2 is equal to minus 1, is equal to e to the minus lambda t2 minus t1 times sin h lambda of t2 minus t1 times e to the minus lambda t2 cos h of lambda t2. P of x of t1 is equal to minus 1, x of t1 is t2 is equal to 1, is equal to e to the minus lambda of t2 minus t1 cos h of lambda of t2 minus t1 e to the minus lambda of t2 cos sin h of lambda t2. So in total we have the autocorrelation of t1 and t2 is equal to e to the minus 2 lambda t2 minus t1. We can see this is only depend on t2 minus t1. So the last problem is r of t1 is t2 is depend on t2 minus t1, but the expected value of x of t is equal to e to the minus 2 lambda t. It's not a constant. So we can draw the conclusion that x of t is not wide sense stationary. That was which to be demonstrated.